Yeah, for those of you who haven't heard of CNI or Colin Nicholas, we've been around in Tucson for about a little over 30 years. We're a geotechnical, boy, those lights are bad. Geotechnical engineering company. We work in open pit, underground, block cave, and what we've done over the years is kind of develop a few techniques that we can use for doing the geotechnical analysis using MineSight. And one of the biggest, I'll go through just say, this is some of the things that I'm going to talk about today. Building geotechnical rock type and block models is kind of one of the biggest things that we do at CNI by taking different rock types and alterations and geotechnical characteristics of the rock. We can subdivide the rocks into certain units that will behave either good geotechnically or bad geotechnically. And what we can do with those is be able to then assign and build a slope angle model that's used by the client and typically used with the pit expansion tool. One of the other things that we concentrate on a lot is defining bedding and how it intersects the pit walls. It's pretty critical in sedimentary units for these deposits that we know what the bedding orientation is so you don't have an adverse bedding orientation to your pit wall. RQD block modeling estimation, very similar to grade estimation, except we use a little bit more lax procedures because we're defining what the RQD really should do, and I'll go into that a little bit more when I get to that part of it. 3D FLAC modeling of rock stress. We use MineSight to code a FLAC model, which is a numerical modeling technique. Modeling geomechanical parameters. In other words, a lot of times RQD, which as long as everybody knows is rock quality designation. Sometimes RQD doesn't really describe what the rock is geotechnically. And by using some of the other geomechanical parameters, we can then model and base everything on our analysis. And fragmentation. We're doing some things with block models and fragmentation that I wanted to talk about. Okay, geotechnical rock type model. Basically what this is just a way to classify deposits so that that we can assign a code that alerts us to some sort of geologic combination. Sericitic alteration along with some rock type that is going to behave differently than another alteration. So the first thing that we're really trying to find out is what really controls the rock quality. Is it alteration? Is it the actual rock type? You know, what's actually controlling what that rock's going to do? We then go in, we define geotechnically similar zones. Well, I'll go through an example and show you, how we're trying to define these different zones and where they lay within a final pit or a phase of one of the pits. When we build these models, we can either use geology or geomechanical properties. We've done them both ways. The geology is really where the basis for all this modeling starts. And then we're coding 3D block models based on the combination of all the geologic factors along with the geotechnical factors. Just a simple example. This is in 2D, of course, but this is going on in 3D also in the block model. You have an intrusive that has a argillic part of it's argillically altered, and geotechnically, you're saying that argillic alteration is an adverse geotechnical parameter. So By doing that, you end up with a geotechnical rock type, whatever it may be. You can then also take what is in the block model RQD and segregate that geotechnical rock type into two separate geotechnically different zones because of the RQD. So you may end up with another geotechnical rock type with a low RQD, the other geotechnical rock type with a higher RQD. It's a way to communicate adverse conditions geotechnically to management or for use in our geotechnical analysis. Once you have the geotechnical rock type model, you can then go in after the analysis is done and break down the deposit into what slope angles are going to be used in different sectors. This is typically based on what the wall orientation of the pits is, and the geotechnical rock types or the actual rock type of the deposit is. The slope angle model is an alternative to the 2D slope template, which is just a 2D thing, whereas when we're putting slope angles into the block model, it is truly 3D and follows the geology. Geotechnical analysis determines the slope angle, and we assign the slope angles directly to the 3D block model using either multi-runs or batch files, whatever you want. And then at the end, the pit expansion tool is reading in the slope geometry. Geotechnical domaining is used quite a bit for basing off of whether the pit wall orientation and domains having to do with the structural domains. So in this case, there's quite a few domains, and we'll make solids or just code from polylines. Typically, because it is in 3D, we'll usually build these domains into solids. One of the things we've been doing with some of our clients is providing them with some alternatives to just one fixed slope angle number, depending on what the wall orientation is. If the mine engineer has the opportunity to change the pit wall orientation a little bit, that puts it in a little bit better stability orientation, then he can use this table. I know it kind of is pretty complicated, but it's actually fairly easy. But he can say that, okay, if he can change his pit wall orientation over here, he may be able to make use of an increase in the slope angle for that certain sector. We typically will give the client the 3D block model that has all the slope angles in it, but then he has the opportunity to be able to change or make use of some of these higher slope angles based on the wall orientation. Just a screenshot of the a typical slope angle model on a final pit. In our field work, we typically do a lot of oriented core drilling, where we're basically getting joint sets, we're getting bedding orientation, we're getting fault orientation. Taking this data and being able to do something with it that will give us an idea of what the bedding orientation is pretty critical in some of the work that we've been doing. We've been using the Geotech tab in the drill hole views, and what it'll do is give us an idea of what, let's say, bedding orientations are really telling us. In this case, we had it was a modeled sediment in here, and we're able to take what we see as the bedding orientation in the drill holes and help the modeler, in this case it was the client himself, help the modeler determine where these low strength shale beds were within that sediment package. And you can see the Schmidt plots over here that show a preferred orientation in this hole right here and kind of a mixed bag here. We actually used some of this data to define that there was actually a syncline in this area that the client actually didn't think was there or didn't know was there. Another tool that we've used with the using the oriented core data is this geosim.dat, where it'll take an input file, just an ID, XYZ, structure type, the dip, azimuth, and length. And the length you can set to whatever you want to, either if you have a longer structure that you want to have more dominant, you can set that length higher and make the disk actually representing the actual the length or the length of the structure. It's all pretty straightforward. Typically, with our oriented core data, there is a lot of formatting that we have to do to get it into this form, but it's still fairly easy. RQD modeling. When we look at RQD, we're looking at not only zones of low RQD, but we're looking at zones of low RQD within an area, a rock mass that may end up controlling that rock mass. Roughly, let's say 20% of the, if 20% of the rock mass is of low RQD, typically that rock mass will act like that low RQD. In other words, it's the weak link. It's the failure mechanism for that rock mass. So when we do RQD estimations, we're typically trying to retain the low-end RQD that is typically present in most drill hole databases. We usually see a bimodal distribution for the RQD. 0 to 10 RQD is very well represented, and we usually have a high end also that is represented. And typically with any estimation technique and even compositing, we're going to start smoothing all that, or spreading that RQD into the middle ranges of the distribution, which we try to keep that that low-end RQD represented, because it's important geotechnically on how the rock mass will actually act. Some of the ways that we're doing that is using indicators for the low and the high RQD, use of a smaller bench composite, which helps in the overestimation of the mid-range RQD, and a lot of times end up loading raw drill hole data right to the composite file so that it helps retain the high and the low RQD and doesn't spread everything into the mid-range. Okay, so Jim will buy you a beer tonight for whoever can tell me which box of core has the highest RQD. It's a trick question. Both of them are 100% RQD by definition. So a lot of times, this is what we find, is that a lot of times RQD doesn't really tell you the whole story sometimes. With these both being 100% RQD rock, this one, you're needing to know where these joints are and what the spacing is. So a lot of times, RQD alone doesn't tell exactly how the rock is going to behave. When either we or we have our clients log their core, we tend to gather not only several different sizes of RQD, but we also collect percent whole core, percent broken, and percent rubble. And the difference between broken and rubble is really just the size. The broken is, greater than half-inch size. So when we collect all that data, we can then also do some modeling with that data. So it's in a case where there is very low RQD. Well, is that very low RQD? What does it mean? What is the size of that material? Is it below an inch, below a half inch? We don't know. By collecting all that additional geomechanical data, we can use that in some of the modeling of the deposit. In the case of this deposit, this is kind of a strange case. The length-weighted mean of drill hole data for RQD on this was 17%. It's more like a dirt than it is rock. So what we found that the RQD being so low, we end up using size fractions. In other words, rubble and broken and whole core being the best of the three. And we also were tracking in the logging process how much gravel, sand, and size, and fines are in the core. In other words, like I said, this is not rock. This is more like dirt. So we track the size fraction of the material that was rubbleized or broken. And by doing that, we were able to map out these zones within the block model. This is just exposed on a final pit. But we were able to use these areas as indicators of where we're seeing such low geotechnical rock performance. 3D FLAC modeling is a numerical analysis or a numerical modeling technique that we use a lot to determine the stress in rock. Unlike a regularized block model, the 3D FLAC model, although it has centroids, the elements that are used in there are not regularized. They're not like a block. They can be any shape or any size that the modeler determines. So in order to get the geologic and geotechnical information into the 3D FLAC model, we need to bring the actual centroids of the FLAC model in as composites. And in some of these cases, it's in the range of 1 to 1.5 million composites. But once we have it into MineSight as composites, we can then back tag the block model geology or geotechnical rock type or RQD, whatever elements that we want to model in the 3D FLAC analysis. Back tag those to the composites, and then export those composites to the for use in the backloading into the FLAC model. A view of the FLAC model with this shows that we can get very good definition in the geologic modeling in the FLAC model that we would be unable to do without without MineSight being able to do that. I'm pretty sure that with our 3D FLAC analysis, we're getting resolution and detail in our models that I don't think anybody else is actually achieving. Next slide is the resulting stresses in the rock based on that geology. Fragmentation. We do fragmentation work on open pits, underground, block caves, and typically with the data that we collect during core logging, like I said before, is we're collecting several different ranges of RQD, several different sizes, and we're collecting percent broken, percent whole core, percent rubble. We're collecting this to characterize the size distribution of the deposit. You know, for you know, all these items, you know, you can just go ahead and read those. But you know, for open pits and underground, this is some of the things that we're looking at helping the client decide. What we get out of the size fraction analysis that we do is basically a distribution curve of the size versus the, you know, the percent less than. This is an example of a block cave with differing heights of draw. But typically for any rock type and or alteration type, we'll end up with a curve. Okay. We'll end up with a curve that describes that fragmentation of those rock types. And the goal here is to assign this curve into the block model so that it can, at any given point, you can determine what the size fraction would be at any given point. One of the ways we've done that is to just use the block size along here as an item in the block model, and our values are going to be points off of the curve that describes the distribution of these. Lastly, now don't take take this too seriously. These are some old final pits from several pits around the world. I put up Sierra Rita there just as a scale. Of course, we know that Bingham, Grasberg, Chuki, Escondida, they're getting to be rather large size. In fact, we have a client right now that is contemplating doing another pushback. Would put them at 1,600 meters pit depth. Which, what this is doing is it's creating lots of data for us. And in the geotechnical end of it and doing the analysis, MineSight has enabled us to filter through a lot of this data. I mean, Bingham's been going for 100 years. Lots of data on this. Grasberg, even though it's only been going for 25 years or so, there's a mountain of data that's being produced at these mines. And MineSight allows us to sift through all this data for our geotechnical analysis. And that's it.